field that is being used as a replacement for animal therapy in nursing homes, which is really kind of awesome.
So she builds planets on Earth, you guys.
Good evening, everyone, and welcome to our very special program, Multiverse, Octave of Light. I'm James Wetzel. My pronouns are he, him, his, and I am the producer of adult programs at the Museum of Science, Boston. I'm coming to you live from our Suit Cabot studio, and I am so thrilled to be collaborating with our friends from the Multiverse concert series once again. We have had the joy of working with them on several shows over the past couple of years, both on-site here in our Charles Hayden Planetarium and also on a couple of virtual events this past summer. And tonight they are back with a brand new lineup to celebrate their brand new album, Octave of Light. And they have an incredible evening of multidisciplinary live performance and groundbreaking research to share with all of us. So it's going to be another fantastic one. And tonight is a part of our current fall virtual season of adult programming. We have just a few events left. We're actually on the tail end of our season. We wrap up with 2 more fantastic events next week. And you can check out full details on both of those and sign up for tickets by going to our website at mos.org/adults. And while you're there, you'll want to sign up for our email list because even though our fall season is wrapping up, our winter-spring season is right around the corner, and we'll be making that announcement very soon. You won't want to miss it. I'll be back a little bit later on for a Q&A with the team from Multiverse. So if you have questions out there watching, you can submit those at any point starting right now by going to slido.com and using the code Multiverse. Once again, that's Slido, SLIDO.com with the code Multiverse. And we'll try and get through as many of those as we can a little bit later on. I need to thank our friends from the Lowell Institute for their continued support in the adult programming. Without them, we would not be here tonight. This event would not be happening, and it would not be free. So please join me in giving a huge virtual round of applause and thanks to the Lowell Institute. And finally, after the show tonight, I ask all of you to go to donate.mos.org/MOS at home and make a gift to allow us to keep bringing free virtual STEM experiences just like tonight into all of your homes. Once again, that's donate.mos.org/MOS at home. But now it's my honor to kick things off and introduce the first piece and the first track in tonight's show, which is Water Romanza. Enjoy.
When I was born, we knew of no planets beyond our own solar system. As far as we knew, we were alone in the universe. And now, over the course of my short lifetime, we've discovered over 4,000 exoplanets. That's planets around other stars. We're living in the middle of an exoplanet revolution, and tonight we want to celebrate that through science, art, and music. I'm David Ibbott, director of the Multiverse concert series, here hosted by the Museum of Science. Welcome to the Octave of Light album launch. Some of you have been following this project for a year, our wonderful Kickstarter backers. Thank you so much for seeing us through. And if you're just joining us, welcome. We began with Water and a piece called Water Romanza, which was the first one that I composed. It's based on the light spectrum of water vapor, and we've been able to detect this on exoplanets already, beyond our solar system. As far as we know, water is essential for life. We're going to be visiting many worlds over the course of the evening, and I'd like to introduce you to our scientific guide. Guiding us on this journey will be Dr. Clara Sousa-Silva from MIT and now Harvard. Over to Clara.
Good evening, everyone. That's all true. I am at Harvard now, and I'm a quantum astrochemist. And what that means is I spend most of my time trying to understand how molecules look like when they interact with light. And I use those tools to try and detect them on distant exoplanets in hopes of one day finding life. And so you have just heard water, and I'll tell you a bit more about how we see water rather than hear water at my work. Could you please start the slideshow? So this is the water molecule, and it's a wonderful biosignature. As David said, it is crucial for life as we know it, but it may be crucial for many different types of biochemistries beyond our own. And I know this is an interesting biosignature because I spend most of my working days investigating interesting biosignatures. Now, water sounded beautiful, but well, and I wish my work was listening to these possible signs of life. But the way we do look for biosignatures is not with sound, but with light. And I'll briefly show you how. Next slide, please. So imagine an alien astronomer on the other side of the galaxy looking for a habitable planet in her night sky. Next slide, please. If this alien astronomer pointed their powerful telescopes at our sun, they would be able to split its sunlight into the sun spectrum, and this is exactly what they would see. Next slide, please. They would see that all of the sun's light, so white and pure, could be broken up into a rainbow, but a rainbow with shadows in it. They would see that some of the light from the sun would have been absorbed by atoms and even molecules that can survive in the cooler regions of the sun and leave behind these tiny dark marks, these absorption lines. And this happens because molecules behave in a really unique way. Next slide, please. Molecules have to follow the same laws of physics as we do, but they're not quite the same physics that we are used to, because molecules are so small that their physics has to follow the rules of the quantum world. And one of those rules, a very strict rule, is that the molecules have to absorb quantized amounts of energy, and these correspond to specific wavelengths of light, and consequently correspond to unique colors in the rainbow that you get from a sun's light. Different stars have different atoms and molecules, and consequently a different spectrum. And this is our sun's. New slide, please. So that alien civilization could look at this spectrum of our sun, and using their universal knowledge of how molecules behave that they got from their quantum astrochemists, know exactly which molecules and atoms were causing these absorption lines and figure out the composition of the sun. But if they were patient and fortuitously aligned, they would notice that every 12 years, new slide, every 12 years, a few additional absorption lines would appear, and then 12 years later, and then disappear, and then 12 years later reappear, and then disappear again. And these new lines will be due to the molecules in the atmosphere of Jupiter as it crosses in front of the sun. And an alien civilization with only slightly better technology than we have now would be able to study these new lines and know that Jupiter has this huge atmosphere of not just hydrogen and helium, but also methane and ammonia, hydrogen sulfide, and many more gases. And if they were really careful, they would notice that every year a few much fainter shadows would appear and then disappear, and a year later return and then disappear. And these, of course, would be due to the molecules in our own Earth's atmosphere also absorbing new lines of the sun spectrum. So that alien astronomer could study these new lines and learn that we are a thriving, complex, living planet. You can think of our atmosphere and its subsequent spectrum as a planet-sized message communicating to the galaxy that we have oceans and cities and varied ecosystems with rich life cycles, and also that we pollute an awful lot. Next slide, please. So these alien astronomers could do this not just for the Earth, but all the solar system planets, and tell the difference between them by looking at the atmospheric spectrum of each planet. If they did that, they would learn that Venus is mostly hell with very high levels of sulfuric acid, though more about that later. And so any life there would have to struggle. And they would also learn that Mars has a teensy tiny atmosphere that can barely shield its surface from radiation, so also not the most hospitable destination. And they would also notice that out of the solar system planets, there's something really special about the Earth, and that's that we have a lot of life. And with our current knowledge and technical abilities, we are at the brink of being able to do the same thing to them. New slide, please. Now, if they had really impressive telescopes, significantly more powerful than ours, they may be able to see one very special and very promising sign of life on Earth. And that is the extraordinary spectral signature of plant life. This happens because chlorophyll is a really strong absorber in the reddest portion of our visible, our optical spectrum. And that causes this red dip that you see in the spectrum. And then the cell structure of the plants, of the leaves, aggressively reflects the light in the near infrared immediately next to the visible, causing this distinctive spectral uptick that you see here in the slide. And this is what the red edge looks like. But now I want to introduce you to a red edge musical piece with the inimitable Beth Sterling.
colors bright like snow. Join me on the red bird. Join me on the red
That was Red Edge, that prominent swoop in frequencies that might show us the presence of chlorophyll and some alien vegetation one day. It featured our soprano for the album, Beth Sterling, but also our stunning violinist, Amelia C., who had quite a few solos in that one. So I just want to say a little bit about this album. It's a concept album in that every piece is inspired by exoplanet spectroscopy that Clara has told you about. So we gather the light from the exoplanets and split it apart like a prism to see the colors. But unfortunately, they have to be represented on a graph, at least visually, because they're not colors our eyes can see. They're spread right throughout the electromagnetic spectrum, and our eyes only see one tiny slice of what's there. One frequency doubling, or one octave of light is what our eyes can perceive. As a composer, I started to wonder, well, if we can't see exoplanets with our eye, perhaps we can hear them. Compared to the eye, the ear has got a massive 10 octaves, well, 10 if you've got very young ears, which is even more than what I have on my piano here. So that's a huge increase in perception. And I started to think, well, why don't we take these frequencies of light and turn them into frequencies of sound? My initial collaborator was Roy Gould at the Harvard-Smithsonian Center for Astrophysics. And he introduced me to the field and helped me to find these absorption lines, these important frequencies that show us what's on a planet. We started with water, and you got to hear that spectrum. The notes you hear when I play a G, it really is a G. It's just I have to shift it down about 40 octaves to be able to hear it. But we can perceive much more of what is actually there. So we've heard the water vapor spectrum. And next, we'll explore the atmospheres of methane and oxygen.
it would quickly combine with methane. To find them together would likely suggest they are continually replenished by living.
I want to say a little bit about the visuals and artwork for our album. You've been seeing these incredible animations created by the museum's Charles Hayden Planetarium animation team. Jason Fletcher, Wade, and Chuck have created this incredible set of backdrops for the music, and they've really dived in deep to the concepts. In addition, our album art is created by Polish science artist Marlene Bochian-Hewitt. And you can see her images behind me, and there's our album cover. We're going to show you a few more. She's created an image through poured art for every piece on the album. And we hope to exhibit these paintings in a public gallery as soon as we're able. Our next piece is called Wanderers, inspired by Carl Sagan.
Darkness, darkness, immortal. began as wanderers. We began as wanderers. We began as wanderers. We are wanderers still. We have lingered too long on the banks of the cosmic ocean. We began as wanderers. We are wanderers still. We have lingered too long on the banks of the cosmic ocean. We are ready to set sail. We are ready to set sail.
That was Wanderers, which featured, as well as Beth Sterling and Amelia C., Exoplanet WASP 17b, which gives us that chord that runs through most of the piece. I'm thrilled to be passing back to Clara now, as well as being wonderful at introducing and sharing people their first experience with exoplanet science. Clara also works at the cutting edge of exoplanet research and has recently announced some amazing discoveries. Right before we finished production on the album, Clara had an announcement for us all. She studies a very special molecule called phosphine, which is tied up with life. Well, she'll tell you more about that. But right towards the end of production on the album, we learned that phosphine might be present in the atmosphere of our planetary neighbor, Venus. And I wanted to do something musically, and I was able to, the same as the others, create a sonification of phosphine. And this is what it sounds like. Over to Clara.
I love the way phosphine sounds, so thank you for that, David. You can start my slides, please. So you just heard the phosphine spectrum, and this is what it actually looks like, the little molecule with one phosphorus atom and 3 hydrogens. But when we look for this molecule or any other molecule in space, what we actually look for is its actual molecular spectrum. Next slide, please. So this is what phosphine actually looks like. And I know this green line very well because I spent the majority of my 20s computing a complete quantum chemical simulation for this molecule. What that means is that this single line you see is actually composed of many, many dots, each dot corresponding to the position and intensity of every absorption line that phosphine leaves in the spectrum of light if it crosses past it. And I calculated 16.8 billion of those transitions, of those absorption lines, which is very hard. But now it means that we can spot phosphine on any distant world that we want. But why would we want to detect phosphine? Well, phosphine is a very special molecule. Next slide. Thank you. So phosphine was known for the majority of time that I've known it as a marker for violent storms on Jupiter and Saturn. So in these planets, phosphine is detected in the observable layers, but it is kind of weird finding it there because phosphine is extremely difficult to make. And it needs really high temperatures and extremely high hydrogen pressures to be made spontaneously. But what happens in Jupiter and Saturn is that phosphine is made in the hellish depths of these planets where there is enough temperature, enough hydrogen pressure for it to be made spontaneously. And then it resiliently makes its way to the top by being dragged by violent storms And it survives with several orders of magnitude more abundance than we would predict by our models. So, phosphine is very interesting, but next slide, please. On Jupiter and Saturn is a sign for storms, but on Earth, it makes no sense to have it there at all. Phosphine is never made accidentally. In fact, on Earth, phosphine is only known for being a horrific molecule. It's a really effective killer, so it's widely used as a pesticide, as a fumigant. And sadly, because it's such an effective killer, it was also used as a chemical warfare agent in the First World War and most recently by ISIS. So humans make it mostly for terrible means, but not just humans. Phosphine is extremely toxic, but only for life that makes use of oxygen metabolism, which is, admittedly, most life on Earth, ourselves included. However, there are a few biological niches that are populated by anaerobic life that is not reliant on oxygen. And on Earth, these environments exist, though they're poorly studied. And here, phosphine is not so evil. Next slide, please. So we find phosphine on Earth in places such as sewage and marshlands, rice fields, lake sediments, the intestinal tract of fish, the intestinal tract of babies, the feces of penguins, the farts of badgers, and actually the intestines and excrements of most animals, because that's where anoxic life lives. All of these ecosystems host life that has no need for oxygen, and for them, phosphine is not toxic. And for the majority of time that life existed on Earth, it also didn't rely on oxygen, which made me think other planets with life less oxygen loving than that on modern Earth could happily have phosphine as a biosignature. So, next slide, please. I imagine this distant, exotic planet, not unlike the early Earth during the Carboniferous period, but without oxygen in the atmosphere. So, a wet, anoxic, tropical paradise with a rich anaerobic biosphere producing tremendous amounts of phosphine. And I worked out that it would be possible to detect phosphine on these distant planets, but it would be really difficult. And I was working really hard to figure out which telescopes could do it and how long would they have to observe each planet. And I concluded that phosphine was a promising biosignature on a few of these exotic, hypothetical, generic exoplanets. And you might now know, partially because David just said it, that this was a naive attitude. Because a few months after I submitted this work, proposing phosphine as a way to search for life in very, very faraway places, I got a weird email from an astronomer called Jane Greaves from Cardiff saying, next slide, please. I think we got a weak signal from the clouds of Venus, the only potentially habitable place in the whole planet. And I think the signal might correspond to phosphine. Is it weird? I think it's weird. And I told Jane what I'm telling you. It is weird. It makes no sense. In fact, the only way we know how to make phosphine on any rocky planet, Earth or Venus, is through life. So this made us very excited, and we spent the next year and a half working very hard to first confirm the signal, which we did with ALMA, which provided the signal seen here in orange. And that seemed to confirm the signal we had from JCMT, the original telescope, which you can see here in white. And we spent a long time trying to figure out, next slide, please. Is the signal really phosphine? And if it is phosphine, is there really no way of making it without life? Next slide, please. Well, we considered dozens of possible non-biological formation pathways for phosphine, and none could be responsible for the amounts of phosphine that were seemingly being detected in the clouds of Venus. So at that point, faced with the exhaustion of all abiotic means of production, we seized on the possibility that phosphine, if it is there, might in fact be produced by life. Now, there's still much about Venus we don't understand, but for now, with the data we have and our understanding of Venus and phosphine, this is what we do know. If the signal is real and it is phosphine, all we really know is that, next slide, please, something really strange is happening on Venus, some exotic, unknown chemistry. Now, whether it's an exotic, unknown biochemistry, that's something for us to figure out with the rest of the scientific community. But whatever the outcome, this is an extraordinary moment for astronomy and for my little molecule. Next slide, please. So now we can look for phosphine on planets all over the galaxy, but the lesson here is not that we should look for phosphine, but that we shouldn't ignore signs of life that differ from the signals that we and life that we find pleasant might produce. We often think that astrobiology is an impossible field of study because we only have one data point, only one planet with life. But that's not really true. Even on modern Earth, we have life that loves oxygen and life that avoids it. And those life forms produce totally different biosignatures. And throughout the history of life on Earth, life has changed drastically, and our biosphere has changed drastically with it. And if any alien astronomers in the last 4 billion years have been watching us, they will have noticed that, next slide, please, Earth has been many planets. As different life forms dominated and released hundreds of different gases into our atmosphere, they sent new spectral messages to the galaxy describing the popular biosignatures of their time. But now, instead of me showing you what they would have seen, David will instead demonstrate that if Earth had been many planets, this is what they sound like.
That was series about not a planet but an asteroid where we've detected ice through this spectroscopy method, and in the next few years we may be able to check that hypothesis and visit and see whether the ice is really there and if our method is right. The next track is called Equals Life, and it's really the central thrust of the album. It's a 4-chord song, and I'm sure you've all heard one of those. But in this case, the 4 chords are the 4 clues that are within the other tracks on the album. The first one that you've already heard several times is the water vapor spectrum. We then move to methane for the second chord. Third, the oxygen single note for a simple molecule. And finally, that red edge for the 4th chord. We can see these clues for life as we know it in our own atmosphere, looking back at Earth as a dot from space. And we have the technology. It's within reach to see these signs on exoplanets and detect life as we know it, or perhaps something even more interesting. Equals life. Water, methane, oxygen, red edge, water, methane, oxygen, red edge.
Red edge. Water. Methane. Oxygen. Red edge.
We end, as we began, with water. This one's for Sarah. That's our show. If you have enjoyed what you've heard, we really want to stay in touch, and everything you've heard is on our website, octaveoflight.com. You can listen, you can get the artwork for our album, the t-shirts. We also have a book of music, the Science Songbook, where you can play the songs. They're all for piano. We're going to go for our question and answer, but I have a huge number of people to thank first. Start off the Museum of Science team, their subspace program, our incredible friends to Multiverse. I want to thank Bethany Zeitz and James Wetzel of the subspace team for making this incredibly ambitious program possible. I've got to thank my fellow musicians who worked with me for many months to make this possible. Beth Sterling, soprano, who joined us remotely, and Amelia C., violinist. For the visuals, we had our album artist, Marlena Birkin-Hewitt, the album cover and the whole gallery, the animators from the Charles Hayden Planetarium here at the museum, Jason Fletcher, Chuck, and Wade, who made all of the beautiful music videos you saw. Of course, our guest scientist, Dr. Clara Sousa-Silva, who gave us that real tantalizing glimpse of a future of discovering life, perhaps next door in our solar system. And to you, Kickstarter backers that followed us and believed in this project and helped us make it a reality. Thank you to everyone. I'll now pass over to James for questions.
Thank you, David. And I'm back, and almost the whole gang is here. We're, of course, missing Amelia, but thank her for her incredible performance. I'm here, of course, with David and Clara, and joining us on the live stream for the first time, Beth Sterling, the amazing vocalist who you've seen and heard all evening. Hello, you three. How are you?
Good.
Good. Great.
A little
Take a
tired.
deep breath. Yes, take a deep breath. I want to thank you all for being here, for sharing this incredible work and your talent with us and our audiences. People are loving it, and it's just been a joy to watch. I do want to jump right into the Q&A because questions are coming in. Before I do, all of you out there watching, I'm sure you have questions. If you have not submitted them yet, you still can by going to the link on your screen, slido.com, slido.com, and enter the code Multiverse, and we'll try and get through those. The first question is one I'm going to pose to all three of you, and we'll go around. But I'm always amazed in these shows how well and how beautifully the art and the science fuses together. And I'm just curious about what that process and that experience for you all has been, especially Beth and Clara, you know, looking at your work through these different lenses. So what has that experience been like? Let's start with you, Beth. Are you muted, Beth? All right, Clara, why don't you go and we'll try and figure out if we can get Beth back on here.
So for me, it's been a wonderful experience because the work that I do in quantum chemistry, it's really invisible to the eye. And so I spend a lot of time putting a lot of effort into trying to visualize what I work on. But I never really dreamt that one day I could hear what I work on. So I'm extremely thankful to David for literally opening up my senses to my own work. So that's been really delightful.
Well, the pleasure is mine, Clara. I feel like I scratch the surface every time I do one of these projects. And, I thought you get that initial sense of, I understand something profound, quite near the beginning of the creative process. But then shortly after, you realize this field is absolutely huge. And you tell me, how many molecules are you looking for on exoplanets? It's in the thousands.
16,367.
So I can't write a piece about all of them. I have to choose.
Yeah, phosphine is only one of those, so it's a long labor. But phosphine is really kind of disgusting in many ways. It smells terrible. It's impossible to see, and then it sounds beautiful, and it's really nice. It seems like such a redeeming feature for this little horrid molecule that causes so much havoc.
That's great. And Beth, let's try. Can we go back to you? Oh no, technology. It's a live show, folks. Well, we'll keep trying to get to the bottom of that. David, how about you though? What is this? I mean, especially approaching this is a full album. So what has this process been like?
Well, it's the largest project I've attempted, and it began from that single piece, that Water Romancer, and I didn't know it was going to be an album, but it just came out so well, making these harmonies out of the planets. We see them as a dot, just sort of a single pixel, and it's something so far removed. And this is this is why I love music, because it can make things real that are far off. It can bring them right into the present moment, and that's really been the goal, is to try to bring the science and the exoplanets closer, because it's something that we're all invested in. It's an incredible achievement that we've made it this far, and we've found the planets, and we're just so tantalizingly close to existential discovery. Are you back, Beth?
Testing?
Yes, we have you
Yay!
back.
I'm sorry
Special
about
moment
that.
there.
That's great. So Beth, welcome. I'm hoping you heard the question, but what has this experience been like for you as an artist, sort of using your art to examine this really intense scientific research?
It's been incredible. I mean, I never thought that as a singer, this would be something that I'd get to be a part of, like something so heavily to do with science. And I've really learned a lot through the process as well. So I have David to thank for pulling me into this for sure. It's not something I would have thought of on my own. So it's been such a great opportunity, and seeing it come to life on the screen with all of those wonderful animations, and like just learning even more about what I've been singing about this whole time has been incredible.
That's great. All right, so I have whoa, the questions are coming in. So let's jump right in. David, there's a question. Someone heard a heartbeat sample. Were there any other specific sound samples in the album?
Yes, there are some heartbeats in there, prenatal heartbeats. I think they're talking about a moment in Equals life. So I sort of that one starts with this quite specific sort of data set, but then I really just let my mind wander into life, and I have two young kids, Lawrence and Eleanor, and we recorded their prenatal heartbeats, and they find their way into the piece in the sort of mix-up section in the middle. They're mixed up in the journey. I wonder if Lawrence will be an astronaut. He certainly wants to now. So yes, you've probably heard them. If anyone's had kids, you'll have heard those sounds.
And Clara, a question about how did you begin in quantum astrochemistry, and any tips for any aspiring quantum astrochemists out there watching tonight?
So I've wanted to be an astronomer since I can remember, really. I do remember the exact moment I decided to become an astronomer. I was 12 and I was watching a solar eclipse with my parents, and my mom, who was always late for everything and for whom time meant nothing, was telling me the really precise moments that every stage of the eclipse was going to happen. And I was so confused because there was no way it could come true. And then it did. It was like my mother was the most powerful being on earth. And I was so impressed. And she explained that she got all that from people who get paid to know the heavens. And I decided then that was it. I was going to be one of those people who get paid to know how the sky moves. And so that was how I did it. But particularly when it comes to the sort of work that I do, which is looking for life, quantum astrochemistry is only a tiny piece of the puzzle. If you want to become a quantum astrochemist, you need to learn quantum physics and care about aliens. I would say that's your only things you need. But if you want to work in my field, you can be a mathematician, an engineer, a graphic designer, programmer, and so there's a biochemist. So there are loads of a musician. And so there are loads of ways of getting into it, because looking for life is a multidisciplinary process, and so it takes a village.
And Clara, we're going to stick with you for another question. how to be sure that life is the source of the phosphine on Venus? Does a probe need to be sent there? Are there plans to get definitive proof?
So we're not sure. Right now, we're going through a really exhausting process of thinking of every way that it cannot be. So we have looked into just all the chemistry and all the thermodynamics that we know, and nothing can make phosphine. Then we looked at maybe reactions with the sun's radiation that could make phosphine. Then we considered where if there are loads of volcanoes and lightning or tectonic plates on Venus that could create extreme systems that could make phosphine, and that couldn't make phosphine. And proving a negative is very hard. So we'll continue to think of more and more implausible ways of making phosphine and show that they can't. At one point, it's kind of the Conan Doyle line, which I don't remember and will probably destroy here, but it's something like when all of the impossible solutions have been excluded, then all that remains, no matter how implausible, must be the truth. That's how we get to life, by excluding every non-life option. We're pretty close, which is really exciting. But inevitably, what we have to do is look for other sources of life. If it is life, it won't just be producing phosphine, and it won't be just one type of microbe. It will be a whole ecosystem with their desires and drives and metabolites, and phosphine is just one of them. So the next step is figuring that out, and that's exactly what we would do on exoplanets. Because Venus is next door, we can go and check definitively, but I would say, one, that should be the last resort because it's very expensive, and two, that should be the last resort because we may harm them and they may harm us, and I don't want the first act we commit as after finding the first life form outside the Earth to be a mass murder. If alien astronomers are watching us right now, I don't want them to be disappointed in us.
It's just really exciting and incredible to have you here tonight talking about all of this. It's fascinating. But I'm going to move on to Beth. I guess before I do that, I mean, there's just tons of love coming in to all three of you and to this experience. So I just want to preface that. And someone saying, Beth, you are so incredibly talented. Wondering, what was it like to sing lyrics that, when written or spoken, might read more like a chemistry lecture?
Well, that's a good question, actually. I think my job as a singer, and anyone's job as a vocalist, or anyone that puts text to music like this would be singers. You have to make it emotional somehow. So a lot of the words did have to do with, they might be something that you'd hear in a lecture, and maybe they're a little bit dry, but you have to inject some kind of emotion into it. David helped a lot with this because his music is so lyrical, and it was really easy to take that and to draw feelings out of it. So I tried to use that and my own experience as a singer to sort of inject this sense of wonderment and amazement into the lyrics that I was singing. Not too difficult, actually, because I felt very amazed by the science behind it. So just using my own natural reaction to it helped. We also approached some of them as if they were similar to, love songs, or in the same style as popular songs you hear on the radio. Most of what human beings sing about are wanting something or loving something. And the science of exoplanets, I think, encompasses both of those.
And speaking of lyrics, David, someone is wondering, wonderful work. Who is the author of these lyrics? Who wrote these lyrics?
Well, it's mostly me, but there's a lot of adapting. So, yeah, I mean, some of them are just the vocalese. So that's where she's just singing one word, methane or water, and we just sort of stumbled into that. We got the notes came out of the data, and she doesn't. They speak for themselves without lyrics. But then the ones that are songs, Red Edge. Roy Gould has a book, The Universe in Creation, and he has a whole chapter on Red Edge. So I was kind of stealing bits from there, and there's some of my own thoughts in there. So yeah, this is the first time I've needed to write lyrics. I mean, adapting it from, there are bits of lectures in there. There's sort of paraphrase Carl Sagan in Wanderers. with sort of some of mine in there. Equals Life is all me. So it's a collage, I would say, and it's a new thing for me. I really enjoyed it, so I'm going to be doing more, I think.
And then a follow-up for you, David. While sonifying the chemical signatures for musical cues in this concept album, how did you decide on which notes correspond to which specific chemicals' light spectrums?
Well, the central link is that light and sound are both waves. So we can talk about light in colors and music as notes, but if we look at them scientifically, they have a wavelength and a frequency, and the frequency is how fast are they oscillating, how fast is the wave moving, and that's exactly the same idea for light and sound. So you can take a light wavelength and in theory turn that into a sound, but light moves much faster. So you have to bring those wavelengths down into the human's audible range, which is pretty wide, sort of the whole concept. Some of the molecules give you a very clear sort of a pinpoint frequency direct from the light. I can turn that right into a note. Other times it's sort of more of a gentle curve, and then there's some artistic decisions that come in. I have to decide, am I going to make that a musical cluster that sort of follows, like the red edge is a it's not a point, but it's a shelf. So I have to sort of decide, and there's no reason it should be sort of rounded to the notes of the piano. That's a decision I made, and you could very easily do it another way. There's always a balance between portraying the data as accurately as you can, but also communicating. And what I like is that the notes are the same. So water, you can hear the notes of water within some of the exoplanets. They stay the same, and those relationships are preserved for the complex spectra and the simple ones that you can take out.
And I want to squeeze this one in here because I think it's a great question again for David. How do you keep your ideas together but open as you're composing a piece? I find as a young composer that when I try to work electroacoustically, I often end up feeling either directionless or trapped by what I've already made.
Oh, well, that's perfectly normal. Well, you need an anchor for it all. I mean, it's unlike science, which you might inherit a question at the beginning of your field, and then you'll ask your own questions. Music, you can get that absolute blank canvas, silence, and it's terrifying. So, I mean, the reason I haven't produced a full album until now is that I didn't have a focal point that made me want to create something of this scope. And thank my lucky stars, I stumbled into science music and then this incredible field of exoplanet research, which it really opened itself up after water. There were all these other elements, molecules that were of interest, and they gave the spectra. I calculated all the chords before I wrote the music. So initially it was just a set of chords, and it was fairly easy to figure out. Okay, well I had to do something about red edge, and I want to do methane has got that really interesting kind of major minor thing going on. So that's got to be a piece. So I think for me, music, I don't like it when it's divorced from the world. It has to reach out and connect with the rest of the world. And if you do that well, then a new world will open up, and the chapters will start to write themselves. If you find that focal point, what inspires you?
And I think this is a great question for us to wrap on, and again, it's for all three of you. It comes from, I believe, a friend of Multiverse and ours, Meg Anderson.
Hi, Meg.
Who's just raving about the experience, but wants to know what was everyone's favorite part of making this album. And I'm going to open it up a little bit. And for Clara, what was of this experience of putting the show together? So let's start with you, Clara.
So for me, it was realizing that I had totally missed the connection between the fact that molecules vibrate, and that's the crux of all my work, figuring out exactly how they vibrate and spotting that, and the fact that these vibrations are also how sound travels. And so to then actually be able to hear the sound of something I've been working on in silence for well over a decade, it was my favorite bit of everything here.
And Beth?
Yeah, so my favorite part is very similar, actually. It's that moment, like the very first time I heard sort of the demo mixes of everything together, I think was my absolute favorite part, because the way David and I had been working on it, we did the majority of the album after coronavirus hit, so we had to do it all socially distanced. So a lot of the times when we were working on the demos, I only had my line to work off of, and I didn't really have a good idea of what exactly the entire piece was going to sound like when it was put together. So that moment that I got the first like email with here's the finished demo with like a little bit of an explanation about what everything meant and the science behind it, and then being able to hear that and hear my own part in context with it was really amazing. It really made me feel like this was going to be something really good, and I was glad to be a part of it.
And David, I mean, this is a labor of love. So
Yeah.
any favorite part of the album or this experience?
Oh, well, it's got to be right here, right now, in the studio with you, James, and you, Clara, and you, Beth. And I only wish more of our friends and the audience could be here in person. And we're going to be out. I mean, this was written to be a live touring album, and we're going to. We're going to share it. Well, there's many people who want to hear it. That's the plan. And Clara, I hope you'll join us.
Absolutely.
Come on the road.
Well, this has been such a wonderful evening. Before we wrap up, David, any final remarks? But where can people buy the album, and where can people support Multiverse and future projects?
Well, I'm glad you asked. So we have the album website. It's just octaveoflight.com. And if you want to support us, you can download the album. And if you want to support Marlena, the artist, you can get the T-shirt, and also a songbook, a science songbook, where you can play the pieces yourself on piano, which we made for our Kickstarter backers. Thank you, all of you, by the way. You're incredible human beings. But we have a few left. Multiverse is an ongoing project, and we work with different scientists and different musicians. Our next event is on the 8th of December. It's free. And we're going to be talking to Bonnie Fleming of Fermilab. So don't miss that one.
Great. And just a special shout out to Marlena. I'm obsessed with this album cover. I have been since the moment David showed it to me, and all of the incredible artwork. So I just wanted to give that shout out. It's just a really wonderful piece of art. So thank you to all three of you again. Thank you to Amelia, the entire Multiverse team. As always, this has been such a fantastic process and evening and fusion of art and science and technology. And we thank you. We can't wait for more. I want to thank our friends at the Lowell Institute once again for making tonight possible. And of course, to all of you watching at home and spending your Thursday night with us. We hope you will continue to do so this fall and for our upcoming winter-spring season. Until we see you again, though, stay safe, stay well, and everyone have a wonderful night. Thank you.